Hello, my name is Aditya, and this is our presentation for the topic Boson sampling in a tunable circuit. Let me start with the introduction. Before explain, Before exploring the specific experimental setup and calculations detailed in the paper, it is essential to understand the theoretical foundation that motivates this work. The paper addresses one of the most profound open questions at the intersection of physics, mathematics, and computer science. That is, the validity of the extended Church-Turing thesis. And what is the extended Church-Turing thesis, you might ask? This is a fundamental tenet of computer science. It asserts that any computational function on a realistic physical device can be efficiently computed on a probabilistic Turing machine. In simpler terms, it assumes that classical computers can efficiently simulate any physical process in the universe. And with this comes a fundamental trilemma. The very existence of the Shor's factoring algorithm poses a fundamental trilemma, suggesting that at least one of the foundational tenets of physics, mathematics, or computer science must be untrue. Shor's algorithm states that efficiently factoring of large composite numbers can be performed on a quantum computer, which is theoretically thought to be realistic physic- physical device. Because factoring is presumed to be computationally intractable for classical systems, we are left with three distinct possibilities. That is, the first being physics breaks down. A scalable quantum computer is not actually a physic- realistic physical device, perhaps because quantum mechanics fails to hold for a large number of qubits. The second one being the mathematical theory is incomplete. If scalable quantum computers are realistic and the extended Church-Turing thesis is correct, then a classical efficient factoring algorithm must exist. The third being the computer science must be revised. The extended Church-Turing thesis itself is fundamentally wrong. Currently, there is no physical evidence that quantum mechanics breaks at scale, nor is there any mathematical proof of an efficient classical factoring algorithm. This leaves the scientific community to critically examine the validity of the extended Church-Turing thesis. Now, how do you resolve the trilemma? To directly contradict the extended Church-Turing thesis, one would need to build a physical device capable of efficiently performing a task that is strongly believed to be intractable for classical computers, while building a universal quantum computer capable of running Shor's algorithm at scale is technologically out of reach right now. This paper provides an alternative route. Rather than engineering a universal quantum machine, the authors experimentally perform a specific highly non-classical scattering task. Scaling this particular task to large number of photons is a much simpler engineering challenge than building a universal quantum computer. If this specific task can be scaled up to a regime where classical verification is no longer possible, it will provide strong evidence against the extended Church-Turing thesis, e- efficiently resolving the trilemma. Now the mathematical core, determinants versus permanence. To understand this specific task that challenges the extended Church-Turing thesis, we first need to look at closely related mathematical concepts, the determinant and the permanent of a matrix. For a n by n matrix A, the determinant is defined using the Leibniz formula, which sums over all the possible permutations of the symmetric group S of n. as you can see here. Here, the signum is the sign of the permutation, plus 1 for even permutation and minus 1 for odd permutation. Whereas the permanent of a matrix has an almost identical definition, but it simply drops the alternating sign, as you can see here. Despite their striking visual similarity, there is a single change, dropping the permutation sign. This results in a monumental shift in computational difficulty. Now we understand the complexity chasm. Polynomial versus exponential. Because of alternating sign, the determinant possesses geometrical properties like representing the signed volume of a parallelepiped and the algebraic symmetries. These properties allow us to use row operation, that is, Gaussian elimination or LU decomposition, to calculate the determinant in n cube time. It is highly efficient polynomial time operation on classical computers. The permanent, however, lacks these symmetries. You cannot use Gaussian elimination to find a permanent because adding a multiple of one row to another fundamentally changes the permanent's value. A naive calculation using the definition requires summing over n factorial permutation, which is O of n factorial times. Even the most efficient known exact algorithm, which is the Riser's algorithm, takes n into 2 of n times. For large matrices, calculating the permanent scales exponentially, rapidly becoming intractable for classical computers. Understanding the intractability NP versus sharp P. To contextualize just how difficult calculating this permanent is, we need to look at classical complexity classes. NP, non-deterministic polynomial time. This class contains decision problems, questions with a yes or no answer, where if the answer is a yes, the proposed solution can be verified quickly. In the polynomial time, for example, the traveling salesman problem, is there a route shorter than x? These are generally believed to be classically intractable to solve efficiently. And P sharp. This is the counting equivalent of NP. Instead of asking if a solution exists, it asks how many solutions exist. For example, how many traveling salesman routes are shorter than the distance x? Problems in sharp P are inherently harder than those in NP because you must count every valid state rather than just finding one. Calculating the permanent of a matrix is a sharp P problem, meaning it is among the hardest problems in the sharp P class. If you could efficiently calculate the permanent, you could efficiently solve all the NP problems and collapse the polynomial hierarchy. Now let's look at the complexity chasm. To calculate for a 2 by 2 matrix, the determinant time takes 0.00053 seconds and the permanent takes 0.00014 seconds. And as you can see, as the matrix size increases, for the 10 by 10 matrix, it is 0.00047 seconds for a determinant, and for the permanent, it's 5 seconds, showing exponential time difference. The true goal of this experiment. It is important to clarify a crucial nuance. The goal of the experiment detailed in this paper is not to build a quantum machine that explicitly calculates and outputs the permanent of an arbitrary user provided matrix. Instead, the paper focuses on calculating a specific physical process, that the scattering of the identical particles through a linear optical network. Quantum mechanics dictates that the problem amplitudes of these multi-particle scattering events are directly proportional to the permanent of various n by n submatrices. By physically running this experiment, this device naturally samples from this highly complex probability distribution to simulate this exact same sampling process on a classical computer. One would have to calculate these Sharpe complete permanence over and over again. As this number of particles n grows, the classical simulation is choked by the exponential math, while the physical device generates the sample simply by letting the natural physics play out. Next, we look into the physics of the boson sampling.
So, hello, my name is Ujjwal, and now we will be discussing the experimental part of this paper. So, we saw how Alice and Bob are in some competition where Alice is classically computing the probability distribution of n photons going through, and Bob is doing it through a photonics setup. Now, we will see how Bob's photonic setup is being made. So basically, we want to make a setup where we take a n Fox state to be as an input. So first of all, for that we need a photon source which can create photons simply, and then we need a linear optical network, which basically which is just a unitary U, which uh, which is the experimental whole setup of our of Alice. So here we will go deeper into it, but here we can see that we have in six input modes and six output modes for n two photons and n three photons. So now we will need a also detection unit to detect those the coincidence or the probability distribution of photons. So now we will see how the experiment is actually happening and what are the different element that is being used. So first of all, we have a photon generation stage, which include first of all a TI sapphire laser, which is a four-step laser, so which gives us a around 820 nanometer input output light. So now using that, we pass it through a second harmonic generation, which is LBO, uh, which is just a lithium triborate crystal. So what it does is basically it is a bifringent material. So it takes the laser light of 820 nanometer as an input and gives us a 410 nanometer output laser. So how is being done is already discussed in our classes also, but we're simply going through it. So the albu crystal is kind of tuned at some temperature, right? We should find at a precise angle so that a phase matching condition is being fulfilled. So at that phase matching condition, we will get output of 410 nanometer. So now the third part in this generation of input, we have a SPDC part. So where we are using a BBO crystal. So what it does is takes a 410 nanometer UV pulse as an input, and through SPDC, a single high energy UV photon probabilistically splits into a pair of lower energy photons, which is 820 nanometer photon. Now we were wondering why we did this. We first already had the 820 nanometer photons, but we needed to kind of correlate them. So what this is what SPDC do. So now after this, we will have short a photon pair going into this, which is correlated. So here they are correlated through these kind of the energy conservation equation and our momentum photon momentum conservation equations. So now there are some other things also. So experimentally, they use two BBO crystal to generate two pairs. So for total four photons total. So where the one photons is used for kind of as a trigger so that we know okay so now the photons are going into the setup. this is to prevent some noise. So if we keep the setup open for all the time, the noise can affect it. So we just open it at the time when we detect the trigger photon. So uh, basically the highlighting the basically the correlated, so we get the info of the other photons also. So now we will see how we are introducing a time delay into our system. So basically, so to time delay, we can, these are just light particles, so we can just increase their path length, optical path length by some refractive, high refractive medium or by some fiber optic cable. So this is what they are using. But what we should keep in mind is that that delay should not be greater than the coherence length of our system. Because if it is, then they will not interfere at all. Then there is no use of it. So the quantum interference part, the Hongo-Mandel effect that we see in particularly two photons, occurs if the are fundamentally indistinguishable. That means they should be in that coherence length region. Otherwise, we will be able to distinguish them typically. So in the Annie's two case, how we do it, we just basically put some delay and we sweep that delay over so that will be a point where we have n zero delay, we will have some finite delay. So we get a kind of a spectrum of of output happening. But there's a problem in three photon case that to coincide three photons using the same sweep method, it is highly unlikely that the three photons will be at the same place at the same time. So this method doesn't work that well there. So we don't use this method, and what we do is just basically we put the delay to be zero and measure it in that way. So now we will see the mode mapping, which is our unitary part, unitary matrix part, which is our core. So in our setup, there is basically three inputs, the three spatial modes going into a unitary machine. We are getting a six spatial mode as an output. But in the but we saw this is a 6 by 6 fully connected unitary matrix, so it should also get a six mode input. So now where are these three extra modes? So these are basically polarization modes that are happening. So each spatial mode also has two polarization mode, which is horizontal and vertical. So there is now the main part of the unitary matrix term, which is our central FBS, the fiber beam splitter part. Basically, what it does is take the six modes as an input and it makes them in such a way that each photon can now go into any of the output six modes. So it basically interfere them in a sense. So the making of it is kind of in detail discussed in this report. So efficiently now, before doing this experiment, we need to know the unitary matrix values, right? Because we are making a system around it. So for that, there is a traditional method, which is a quantum process tomography method. So which requires an exponentially increased number of measurements. So we have to keep repeating a lot of measurements. So it's basically how traditional uh, positron emission tomography happen. We have to take a lot of measurement for it, but in quantum processes this is quite inefficient. So now there is a classical solution that is given in the paper. So there the researchers use a classical laser light, which when falls into the unitary matrix and gets an output, then the intensity of that output we can get all the uij matrix value, their modulus. And to get the phase, here they uses two classical beams simultaneously and they uh, put it in our unitary matrix and they get some output. Now by changing the phase of those input, they can basically tweak this interference that is happening there and they can get the theta 1j minus theta 2j part. Now by putting one reference theta 1j to be 0, they can get all theta 2j, theta 3j and all of these things. So here, this is how we are getting our unitary matrix U also. So now we will see how the theory and experiment part are different in the sense. So Alice was doing using a classical computer by it was computing large permanent values, which is a Sharpie problem as we discussed before. So he was basically building UST matrix from U based on the photon in those modes, but Now we will see basically how the quantum indistinguishable photons give us the result and how the classical part gives us the result. So basically, when we are using quantum part, basically we are in the coherence length region. Then we will take first the permanent of the UST part, where UST is the submatrix of our U big matrix with S and an input state and T what we are getting as an output. So we are creating a submatrix of it, and by getting the permanent, we can get how, like, what will the probability distribution of it in the output mode, because our photon is also just a symmetric sum of all the output of all the states. So permanent also calculate the all the symmetric state of the matrix also. So these are basically correlated. So now how the classically it is happening. So in the classical, what is just happening is modulus is going, the square is going inside. So, and the permanent is outside. So what it does, it destroy the interference term, whatever the interference term that will be in the perm that will be in the UST part. Because if we are taking a modular square, then the interference is gone. So this gives the classical result. Now there are different kind of problems in our setup also. It is a practical system. So to get rid of it, we use a error cancelling solution, which is visibility. We basically subtract the from the classical solution our quantum probability distribution divided by PCT. Now, what it is, all the error that are in PQT will also be in the PCT. So this improves our final results basically. So now we will see a three photon state as an input, and we will see how it evolves through our system. So first of all, we have a photon source that is our TI sapphire laser, and then we have second harmonic generation LBO crystal, and we have a BBO crystal. Then there are some delay lines in our system. So after all of this, we are getting this as an input. Now here we are assuming that all of our photons are in the horizontal polarization mode, and we have put some delay in our one spatial mode and three spatial mode. Now we can put delta T1 and delta T3 to be 0 in this case to simplify it. So now after this delay lines, we have some local unitaries which are polarization controllers of the input state. So what they do is they take the creation operator as an input and transform as it as the horizontal and vertical polarization also. So if in input we only have the horizontal polarization part, in output we will have horizontal polarization and vertical polarization, both of them. So this can be characterized by this AK matrix, and they can be the whole C1 creation operator, C2 as creation operator can be transformed in the same way. Now there comes the main part, which is our fiber beam splitter part, which is actually interfering all of those things, all of the input. So basically what it does, it takes the creation operator CKP at some polarization P, and it sums it over through all its row, basically row value. So if we say C1P creation operator, so that will be the sum of all C1P, C2P, CP3 creation operator, because all the U value in the first row is 1. So this is how it is interfering all of the modes basically. Now we have some output local unitaries also, which are controlling the polarization of the output state. Now one question is why we are using uh, so many different polarization local unitaries. So we want to control that unitary part. Now FPS is something that is fixed, right? But we can change the local unitary by changing the polarization factors of these things. So this way we can control the unitary and get some different outputs also. So finally we have a beam splitter also, and then we measure it using a avalanche photo detector, yeah, APD. So what we get as an final, we can say this is just the five final is just the our input mode, our input zero state is getting multiplied this whole thing. So this is the whole, uh, basically we can say circuit that it is doing, and we have already discussed how it calculate the same thing as permanent, and hence the Bob will be able to get the final results quite quickly by this experimental setup. And now we will discuss some the supplementary part of the paper and some pros and some like difficulties in doing this experiment. So first of all, the SPDC part, it is kind of a squeezed vacuum thing because we can see there is a 0 0 state, then there is a eta 1 1 state where eta is a probability of getting 1 1 state basically. So it can happen if the pump power is too large in our SPDC system. So but we don't want that, right? We don't want higher order two photons, three photons. We just need one photons, right? So for that we use basically we we want to keep the eta value to be a lot less so that eta square, eta cube terms are quite less and we only get 1 photon thing. So for using that, we like use lower pump source, and this is the only solution for it. Like this is fundamentally it gives output like this. The second part is that are there can be different time delays that are due to thermal expansion and all of those things. So it can make the partial distinguishable are photons. It can make them go out from the coherence length region. This is another problem, temperature control and all of this. There is other problem that is photon loss that is due to the detection efficiency that is happening. Like some photon will be detected, some will not be detected due to the quantum efficiency of our APD detectors. So these are some problems. Now we will see how our visibility part actually tackles this problem. No, not all, but some problem. So basically, we have a we are using six detectors now. All of these detectors can be different. We can have unequal detector efficiency. Even if they're same in all of the things, the quantum efficiency can be little bit different due to some errors. So what the actual probability distribution is, that is PT, we will be seeing MT, that is multiplied by the quantum efficiency of our detector. So the net efficiency, we can say it is a multiplication of all the detector efficiency. So this is one thing, but as we the visibility also solve this because uh, the hardware part, that the quantum efficiency part will be cancelled because the VTB box will be MCT minus MQT divided by MCT. So now both of these are quantum efficiency of all of these are same. So hence they will be cancelled out and we will get uh, like quite good better result than before. So how Alice is getting PCT? So he is using like computers, some algorithm to get it. So how Bob is getting them is Bob to get PCT the classical rate, he is just making the photons greater than the coherence length, and it basically gives us the uh, experimental PCT. It's quite logical. And there is some other problem in N3 that we already discussed, but again again. So the N is three part, as we said, if the coincidence count rate is quite low. So we cannot sweep around the value. So the delta T, the delay always has to be close to zero. So that is one kind of con, like we cannot interfere three photons by introducing some delay such that they all are in some coherence length region. So here they uses so uh, basically continuous Kenko, they avoid in three case and rely on a minimal set of discrete measurement points. Basically, they like sacrifice the continuous part and they try to get some discrete values for it. Uh, So to find the we discuss the PQT part. So there the delay they set is zero, and in PCT part the delay that they put is a lot greater than the occurrence length L. So here it is denoted by del tau of infinity. So now what is infinity? Now therefore just like to reduce the error, they first gives minus del tau infinity to photon 1 then and plus del tau infinity to photon 3, and then they reverse this order and take the average of it to get more accurate results. So now there can be cases where we have two photons coming simultaneously at one mode only. These are when there is high intensity happening and some error there is in the system. So basically for this, what we do is we can introduce a beam splitter at the detector side in after the output unit local matrices. So what that will do if there are two photons coming, then that beam splitter will split them into two different part, and we can have 12 detectors actually to measure the coincidence and also the probability distribution. So getting more accurate results in this. But this also introduces some more errors also. So doing this is quite difficult. They have in paper they have just discussed it. I don't think they have completed this experiment whole. So yeah, so this is the one thing, the detection problem there is, and the role of the additional detector is just to get how many photons are there. Like our avalanche photodetector doesn't detect how many photons are. It just gives us a signal whenever there is one photon, 10 photon is coming. So this helps in this. Yeah, so this is all for my part. Thank you.
Okay, so now that we have understood the problem that will help us break the trilemma that we discussed above, let us now see how the problem of boson sampling, uh, we can see natural occurrence of the calculation of permanents, which can help us uh, efficiently calculate permanents and outperform classical competition. So let us assume that the optical photonic network has total of n m input modes as well as m output modes. So in this case, for this particular example, which does not break the generality at all, but is just for simplicity, we have taken n single photons and injected it into the first n input ports, where obviously n is less than m. We can represent this input state uh, as following. Now, as we have also studied in class, the beam splitter performs a unitary transformation of all the input creation operators and converts it into a linear combination of output creation operators, which can be seen as follows. Now, using this equation and putting it into the first equation, we can write the output state as follows. Uh, Now, to calculate the probability amplitude of some particular state that we are measuring, let's assume that the particular state here that we are trying to detect is given by t, where we are detecting specific modes only. Those modes can be uh, termed as k1, k2 up until kn. So this is the output state that we will be measuring. So to find the probability, we must find the inner product between them first to get the amplitude. Uh, Now, another important property is required here, which is that in bosons, the creation operators commute, meaning that we can write uh, uh, AK1 dagger AK2 as well as AK2 AK1 dagger. So this way we can write uh, this output state T as all the permutations of K1, K2 up until Kn, all the possible permutations. And when we find the inner product between T and the output state psi, then we get the following mathematical structure, as we can see, where sigma represents all the possible permutations of k1 k2 up until kn. Now we can this structure seems familiar, right? So if we go above, we can see that this exact same structure is of the permanent of any matrix A. So specifically, in this mathematical structure here, the permanent is being calculated of the n cross n sub matrix of the initial unitary U, and as we can see from this, the probability of a particular uh, output state occurring uh, requires intrinsically requires calculating the permanent of all the n cross n sub matrices. Now, one might say that, well, why can't we use fermions for this case? Why can't we use fermions to solve our trilemma? So let's see what similar calculation brings us in case of fermions. So in this case, another important property is that to follow Pauli exclusion principle, the creation operators for fermions must anti-commutate. This means that if we make odd permutations for any set of uh, creation operators, we get a minus sign in front of it, while for even combinations, we get a plus sign at the end of it. So, doing the similar uh, permutation operation that we did for the boson, we'll find that the output probability amplitude has this plus or minus sign depending on whether the permutation is even or odd, which is the exact mathematical structure of a determinant. So in this case, the probability amplitude depends on the determinant of the n cross n submatrix of the initial unitary U. Since we know that determinants can be calculated efficiently on classical computers, this means that the problem of fermionic sampling cannot be used to break our initial trilemma and challenge against the extended Church Turing thesis. Now, moving forward to clearly illustrate the practical implications of boson sampling, the author has framed the problem as a race between two participants, namely Alice and Bob. So, Alice is our classical contender, which works in the classical regime and represents the extended Church Turing thesis. Meanwhile, Bob is the quantum contender that works in the quantum regime, and instead of calculating the maths, Bob uses the physical quantum resources to efficiently calculate the probability of various scattering events. Now, the particular situation discussed in the paper are the cases where the number of input photons are small, uh, particularly n equals to 2 or 3. In this region, both Alice and Bob will be able to efficiently calculate the resulting probability distributions, and they can thus compare between their results to verify that the optical setup of Bob is working correctly and is indeed intrinsically calculating permanence to give him the actual correct probability of various scattering events. However, the paper also proposes a conjecture that when this n rises up and goes to numbers around 20 or 30, the exponential scaling of classical computers will immediately make this sampling computationally intractable. Meanwhile, for Bob, he has to just let the input 20 or 30 photons in the input ports and let them evolve, which they do at the speed of light, uh, and let them go to the output port and then sample the probability of various scattering events. Thus, using this, we can have a strong evidence against the extended Church Turing thesis. But before we even begin this computational race, there is another problem we have to solve. uh, Bob already has the actual physical hardware, which is the optical network that performs this unitary transformation on the input creation operators. However, for Alice, she must have the exact mathematical representation of this unitary transformation to first find what the total transformation will be and then calculate the permanence of the n cross n sub matrices from that unitary. One solution is that Alice can use Bob's optical circuit and perform characterization of the unitary transformation that the particular circuit performs. Now, the traditional methods include quantum process tomography, but if Alice has to use this method, then she would have failed miserably because the number of measurements that Alice has to make using this method would scale exponentially with the size of the system, which in our case is m. Due to this, the race would be over even before it began because the setup time for Alice would be just as intractable as the computational time. To mitigate this issue, authors have proposed another novel characterization technique which is highly efficient and can be used instead of the quantum process tomography. In this particular process, Alice has to perform only 2m minus 1 uh, distinct measurement combinations to completely characterize the unitary matrix. Another issue that we must focus on is that since Alice is working in the classical regime, she is forbidden from using any quantum resources such as single photon sources and such. Thankfully, this novel process allows Alice to use only coherent states of light to completely characterize the unitary matrix. Since this is a classical resource, Alice has not left its classical regime and the race is still on. Now, let's see how Alice will characterize the unitary matrix with the novel technique that we just discussed above. So, any linear photonics network can be described by the following mapping between the input uh, uh, creation operators and the output creation operator. This mapping is done by a unitary matrix U, and each of its element Uij can be written as uh, the magnitude Rij as well as its phase e to the power of I theta ij. Now let's see how Alice will extract the magnitudes Rij. To do this, Alice injects a single mode coherent state into one of the input modes, let's say I, and she leaves all the other input ports completely dark. Now, Alice adjusts the amplitude of this field such that the intensity is equal to 1. This is done just for ease of mathematics and does not leave the regime of generality. Now, let's assume that Alice is measuring the output port J using the same unitary transformation matrix mathematics discussed above. We can write the output field at the mode J as follows. Now, when we take intensity of this field, we see why we took the intensity of the input field to be 1, and immediately we see that the intensity of the output field at mode J is equal to the square of the magnitude of the input of the unitary transformation element uh, which was used to transform the incoming light from mode I to mode J. Thus, by taking the square root of the intensity, we get the amplitude Rij. Thus, letting the coherent by letting the single mode coherent state into the input mode I and measuring all the output modes, Alice can get the magnitude of all the elements in the ith row of the unitary matrix that she wants to characterize. Now let's see how Alice will extract the phases. For extracting phases, Alice will let two coherent lights into two input modes simultaneously. One of them will be the reference port, which is assumed to be in port 1 in this case, and the another port will be varied. Now, for again mathematical simplicity, we have taken the two coherent lights to be 1 and e to the power I phi. Again, when Alice measures the output mode J, we can write it as a linear superposition of the two input modes. And when we take the intensity of this output, we see that the intensity oscillates as we sweep across the relative phase between the two input modes, which is phi in this case. So as we sweep across phi, this ij will oscillate, and by simply measuring the phase offset of this oscillation, Alice can easily find the phase difference, delta phi. Since port 1 is taken as reference port, Alice varies the other port from k equals to 2 to m. Doing so, Alice finds the relative phase of all the other ports with respect to 1, which is all that is needed because global phases uh, does not have any physical significance. Thus, Alice only has to perform m minus 1 measurements in this case. In the earlier case of magnitude measurement, Alice had to perform m measurements. Thus, the total number of measurements she has to perform is m plus m minus 1, which is 2m minus 1. Now that Alice has successfully characterized the full m cross m unitary matrix that she needs to find the probability amplitudes, let's see how she will calculate the permanent of the matrices to get the actual probability amplitude of a given specific scattering event. In this case, the scattering event is as follows. The input for this configuration will be given by S, which is up from S1 up until Sm, as well as the output for this configuration will be given by T, which will be from T1 up until Tm. Now, given the full matrix U, what Alice does first is filter only the relevant outputs. She does this by taking tj copies of the jth column of the initial matrix U to get the resulting matrix UT. This matrix UT represents the destination of the photons. Then Alice applies the filter for the inputs. In this case, she takes the matrix UT and then takes Si copies of the ith row. This gives her the representation of the matrix UST, which represents the origin of the photons. Now, this resulting UST is the n cross n matrix, n cross s submatrix that we require to find the probability amplitude of this particular scattering event. Now let's understand this by a concrete example. Say if we have a total of 4 input modes as well as 4 output modes, that is m equals to 4, and we are injecting 3 photons into the system. Now for the particular scattering event, we have taken the input configuration to be 1011 and the output configuration to be 0111. Now let's construct UT by looking that the first mode of the output is 0. That means we'll only consider the rest of the 3 columns of the matrix U. This gives us the matrix UT. Again, we look at the input configuration and see that the second mode of the input is 0. This means for matrix UT, we'll consider only the rows 1, 3 and 4. This gives us the matrix UST. This represents all the relevant quantum pathways that we need to find the resulting probability amplitude. Once Alice has constructed this matrix UST, to find the quantum case where she has indistinguishable photons, she must find the permanent of this matrix UST first and then square it to get the final probability. However, if she is working in the classical case where she has distinguishable photons, why we are working in this case will be more relevant when we go deeper into the report, but for now, if she has to find the probability in the classical case, she must first square all the elements of the initial matrix UST and then to then get the matrix UST tilde, and then she calculates the permanent of this matrix UST tilde to get the final probability for this classical case. To show this more concretely, we have reproduced a result that was given in the paper. In this, we have been given the matrix U that characterizes the optical circuit, and in this case we are injecting only two photons in the setup. Particularly, the input configuration was 101 and then the remaining three zeros, and the output uh, configuration was 010010. So looking at this particular configuration, we see from T that we'll only have to keep column 2 and 5 of the matrix U to get UT, and to get UST we keep only the first and third row of UT. This gives us a clean 2 cross 2 matrix that has all the required information to calculate the resulting probability amplitude. To get the final probability, we take the permanent of this matrix UST and then square it to get the probability for the quantum case, and for the probability of the classical case, we square each element of this matrix UST and then take the permanent. As we can see, the probability for quantum case was 0.0017, and for the classical case it was 0.0349. These results matches perfectly with those given in the paper, thus verifying the correctness of our code.
So in my part, I'll go through the figure reproduction section of our notebook. The idea here is not just to show a few plots that look similar to the paper, but to show how these plots actually come out of the boson sampling formalism and the measured unitary matrices given in the supplementary material. I'll mainly focus on figure 2, 3, 4, and 5 because together they tell the story of the paper quite nicely. We take us from basic permanent calculation, 2 photon and 3 photon visibility patterns, then to colliding outputs, and finally to the effect of source imperfection. So let's start with the scope. Before I start with individual figures, I just want to make one thing clear about what is exact and what is reconstructed. The matrix-based calculations in this notebook are directly based on published supplementary material. So whenever we calculate bosonic probabilities, distinguishable probabilities or visibility from the unitary, that part is an exact reproduction of the theory using author's own matrix. The summary L1 values quoted in the text are also included exactly as reported in the paper. For figure 5, the trend is recreated from the plotted graph, so that part should be thought of a careful graphical transcription. And for Bob's individual measured bars in figure 2 and 4, the paper does not provide a machine-readable data table. So what we reproduce here is the theoretical structure of those figures, rather than claiming that every experimental bar has extracted exactly. As you can see here, we loaded the helpers and unitaries. Now reproducing figure 2C, which is 2 photon boson sampling visibility. This is where we begin to see the visibility pattern across many output configurations in the 2 photon case. The paper considers 3 different photon input configurations, and for each one of it looks at how the visibility changes over all possible non-colliding outputs. In the notebook for every one of those outputs, we calculate the bosonic visibility from permanent base probabilities. Alongside that, we also calculate the coherent state visibility using the formulas from supplementary material. So when these plots appear, the bars correspond to the quantum visibility prediction, and the circular markers correspond to the coherent state prediction. What I find important here is not just that the values are different, but the whole pattern is different. The coherent state calculation acts as a classical baseline. If Bob's data followed that pattern, then one could argue that the same optical circuit is just producing an ordinary classical interference effect. But the paper shows that Bob agrees much more strongly with the quantum prediction. So this figure is nice bridge between the basic permanent calculation and yeah, more serious 3 photon boson sampling result. It already shows that even at 2 photon level, the visibility structure is highly non-trivial and clearly depends on genuine bosonic interference. Here you can see all the three graphs. And now let's start with figure 3, which is 3-photon boson sampling visibility. This is really the central part of the paper because now we are in the 3-photon region. This is really the central part of the paper because now we are in the 3-photon region. The notebook reproduces a visibility structure for the same 3-input configuration shown by the authors 135, 146, and 156. Just like before each possible non-colliding output, we compute the bosonic visibility from the measured unitary and compare it with coherent state prediction. But now the structure becomes much richer. Some outputs have large positive visibility, some are suppressed, and some even go negative. This is exactly what we expect in a genuine many boson interference setting, because each output event receives contributions from several multi-photon paths, and all those combine to permanent. So when I present this figure, I'd probably slow down a little and say that this is where the boson sampling idea really becomes visible in the notebook. The 2-photon case helps build intuition, but the 3-photon case is where the main claim of the paper starts to feel much more substantial. Moving on figure 4b, which is 3-photon boson sampling with colliding outputs. Up to this point, most of the discussion is about non-colliding events, meaning each occupied output mode contains only one photon. But in figure 4, the paper deliberately studies outputs where two photons appear in the same output mode. For the input configuration 135, the outputs considered are 155, 255, 355, 455, and 556. This matters because boson sampling is naturally written in occupation number language. So colliding outputs are no longer discrete phenomena. They are part of some formalism. The only technical change is that repeated occupation means repeated rows or columns in the submatrix construction. So this cell is useful because it shows that formalism still works even when the output is more complicated than a simple one photon per mode case. It makes the notebook feel more complete, and it also follows the structure of paper closely. This is where we see figure 4b. Finally, we reach figure 5, which is imperfect Fock states in boson sampling. This is one of my favorite flaws in paper because it connects the theory to a very real experimental limitation. A pump powers a pump as pump power increases, the down conversion source produces more higher order photon number terms. That helps the count rate, but at the same time makes the input style less ideal. The graph tracks how L1 distance changes with pump power. The graph tracks how the L1 distance changes from The graph tracks how the L1 distance changes with pump power. One curve compares Bob's measurement with Alice's ideal Fock state production, and the other compares Bob's measurement with Alice's coherent state prediction. The trend is very telling. As pump power goes up, the agreement with ideal Fock state prediction becomes worse, while the system starts looking closer to a more classical baseline. So this figure is very useful in presentation because it reminds us that boson sampling is not just the abstract permanence, complexity theory. It also depends critically on how well the photon source approximates the ideal input state. To wrap up, this notebook section follows the same logic as the paper itself. We begin with the worked permanent calculations, then move to the 2-photon visibility structure, then to the 3-photon case, after that, colliding outputs, and finally to the source imperfection trend. Taken together, these plots show how the measured unitary, the boson sampling formalism, and the observed visibility patterns all fit together.
Now I will discuss the experimental results of the paper, which is really where the central claim gets tested. Up until this point in the presentation, we have already seen two sides of the story. On one side, Alice has the theoretical machinery. She characterizes the interferometer, obtains the measured unitary matrix, and that from she computes the expected boson sampling visibilities. On the other side, Bob actually runs the optical experiment using photons and measures what comes out of the circuit. So the natural question now is, how do the others decide whether Bob is actually doing the boson sampling predicts? The answer is that they compare Li's predicted visibilities with Bob's measured visibility using an average L1 norm, distance over all tested output configurations. The formula they use is the average over all outputs T of the absolute difference between Li's visibility and Bob's visibility. So if Alice and Bob agrees very well, this L1 distance will be small. If they disagree strongly, the distance will be large. I want to make one point here because it matters for how we present our notebook. These L1 comparison values are given directly in the paper, but uh, हाँ तो अबे ये थोड़ा धीरे धीरे हो रहा है यार तो यहाँ से कर रहा हूँ फिर स्टार्टिंग से नहीं बीच में से करो हाँ, क्या यहाँ से कंटिन्यू करूँ अभी तो बीच में एडिटिंग करेगा ना वही कट करेगा ना तो अभी स्टार्ट अच्छा ये कर रहा हूँ I want to make one point clear here because it matters for how we present our notebook. These final L1 comparison values are given directly in the paper, but the PDF does not provide a machine readable table of Bob's raw visibility values for every output configuration. In the figures, Bob's results are shown as bars, but the exact numerical data behind all those bars are not tabulated in the paper. So for this section, what we are doing is not claiming that we are reconstructed Bob's entire data set from scratch. Instead, we are faithfully discussing the comparisons values that the authors themselves report in the paper and interpreting what those values mean physically. Let me start with the two photon case. As a baseline test, the authors inject two photons into the circuit and look at all possible non-colliding output combinations. Since there are 6 output models, the total number of non-colliding two photon output is 6 choose 2, which is 15. For each of these outputs, Alice computes the visibility from the measured unitary and Bob measures the visibility experimentally. Then they compare the two sets. The result is very strong. The average L1 distance is reported as 0.027. That is very small number and it tells us that Eli's theoretical predictions and Bob experimental measured uh, match extremely well in the two photon regime. But the author do not stop there because agreement alone is not enough. A skeptic might still ask whether Bob is just reproducing something that could also arise from a classical optical field. To test that, the paper introduces what I would call the classical sanity check. Alice also computes what the visibilities would look like if she would coherent states inputs instead of ideal Fox state photons. These coherent state predictions are the classical wave baseline. Now, if Bob measure results were also close to the coherent state prediction, then the experiment would not really establish anything strongly non-classical, but that is not what happens. The paper reports that the distance between Bob's measured visibilities and Alice's coherent state prediction is 0.548. that is much larger than 0.027. So the message is very clear. Bob is not just reproducing a generic classical interference pattern of the same interferometer. His results match the bosonic prediction and much better than the coherent state one. And the authors explicitly say that this large disagreement shows the quantum distribution is sufficiently different from the classical one, meaning the chosen unitary is not some special easy case that is classical description would accidentally mimic. So already in the two photon case, the experiment is doing exactly what it's supposed to do. It validates the permanent base prediction and separates it from the classical coherent state alternative. Now let us move on to the three photon case, which is much interesting and also how more demanding experimentally. Yeah, when the authors scale up from two photons to three photons, the system becomes more complex in two different senses. First, there are more interfering multiple photon paths contributing to each output. Second, the experimental difficulty increases significantly because the source and detection imperfections becomes more important. Again, the authors compare Alice's predicted visibilities with Bob's measured visibilities across the non-colliding output. This is the reported L1 distance is 0.122. So compared to the two photon case, the agreement becomes worse, but it is still clearly good enough to support the boson sampling model. The authors also explain why this distance is large. They attribute it mainly to the increased ratio of higher order photon emission in the three photon experiment. This makes sense physically because the down conversion source becomes more problematic as the photon number increases. It is harder to approximate the ideal input state, and the errors start to show up more clearly. But once again, the important comparison is not only Alice versus Bob. The coherent state benchmark is also included. For the three photon case, the distance between Bob's measured result and the Alice's coherent state prediction is reported as 0.358. So even though the three photon experiment is less accurate than the two photon one, it is still much closer to the bosonic prediction than the classical coherent state baseline. That means the genuinely quantum interference is still clearly present. This is very important part of the paper because it shows that the boson sampling signature survives even when the experiment becomes more difficult and more realistic imperfections are present. After that, the paper goes one step further and studies colliding configurations. Until this point, most of the analysis focused on non-colliding events, meaning outputs where at most one photon exists each output mode. But boson sampling is principle includes colliding output as well, where two photons can emerge in the same output mode. Uh, the authors therefore test those cases too. Experimentally, this requires photon number resolution because the setup must be able to distinguish between the photon in one mode and two photons in the same mode. In the paper, they achieve this using a 50-50 fiber beam splitter and an extra detector. Now, this is more demanding test because the output configurations are more complicated, but the result is again very encouraging. For this colliding output state, the paper reports an L1 distance of 0.153 between Alice's predicted visibilities and Bob's measured visibilities. So even when the agreement is still quite good, and once again the classical sanity check makes the picture even stronger. The distance between Bob's measurement and the Alice's coherent state prediction becomes extremely large, namely 0.995. That is almost maximal compared to the earlier case. So the colliding output regime, Bob's results are still close to the bosonic prediction, but very far from the classical coherent state baseline. This is important because it shows that the robustness of the boson sampling description is not limited to the simplest output class. It continues to hold even in these more complex colliding configurations. So overall, across all three tests, the pattern is very consistent. For two photons, Alice and Bob agreement extremely well with L1 equal to 0.027. For three photons, the agreement is still good, but with L1 equals to 0.122. For colliding outputs, the agreement remains strong with L1 equals to 0.153. And in every one of these three cases, Bob's results are much farther from the coherent state prediction that the from the bosonic prediction. That is really the central experimental conclusion of the paper. Uh, Now let me move to the final part of the section, which is about imperfections and the path forward. A careful reader will immediately notice that the agreement is not perfect. The L1 distance is not zero, and it's get worse as we go from 2 photons to 3 photons. So the obvious question is, if Alice's theory is correct, why does Bob match it exactly? The answer is that Alice is calculating it in an ideal mathematical world, while Bob is working with real hardware. Alice assumes perfectly indistinguishable Fox state inputs. Bob, however, generates photons using spontaneous parameters down conversion or SPDC, and SPDC is probabilistic, not ideal. This introduces two major sources of noise. The first is higher order emission. Even if the source is tuned to produce single pairs, there is always some probability that it produces extra photons. Those extra photons contaminate the intended input state. The second is indistinguishability. The photons produced by down conversion can be spectrally entangled which means they are not perfectly identical. As soon as the photons become even slightly distinguishable, the pure bosonic interference is weakened. This explains why the experimental agreement becomes worse in the 3 photon case. Bob is trying to realize an ideal input state, but the source itself is imperfect. This leads to a very important hardware trade-off. If Bob increases the pump power, then he can generate photons more often, which improves the code count rate and makes data collection faster. But increasing pump power also increases higher order emission, so the source becomes noisier and the output statistics are pushed away from the ideal quantum distribution and toward a more classical looking regime. That is exactly what picture 5 in the paper shows. So the experimental has a built-in conflict. Low pump power gives cleaner photons, but very low rates. High pump power gives better rates, but introduces more noise. And because SPDC is fundamentally probabilistic, the problem becomes much worse as the number of photons grow. The success probability drops rapidly with photon number. This brings up to the final big picture point. This paper does not yet disprove the extended Church-Turing thesis by itself. The system is still too small. 2 and 3 photons are not enough to enter the truly classically intractable regime. But what the paper does achieve is very important. It validates the fundamental uh, physical mechanism of boson sampling. It shows that a real photonic device using a measured interferometer unitary produces output statistics that follow the permanent based bosonic prediction and not the classic coherent state baseline. That is the experimental foundation and field needs before trying to scale up. According to the theoretical estimates discussed in the paper, really decisive regime would be around 20 to 30 photons in a network with many more modes, where Bobs could sample quickly but Alice could no longer verify the result efficiency on a classical computer. Reaching that regime is no longer mainly a question of theory, it becomes a question of engineering better photon sources, lower losses, and more efficient detectors. So, if I summarize this entire section in one sentence, it would be this. The experiment already confirms the correctness of the boson sampling mechanism in small systems, but the final challenge is to scale it into regime where classical verification breaks down and extended church tuning thesis can be tested directly. And that is why these experimental results matter so much. They do not end the race yet, but they show the Bob is clearly running in the right direction. that's all. इतना लंबा फिर बोलने के बाद थोड़ा रुकना होता है बैठ होने के बाद थोड़ा सा हाँ रुका मैं कितना वन वन फिफ्टीन